In this video, we're going to talk about compound random variables, which are also known as random sums. Often we might have a situation where there are two sources of randomness, both contributing to a random variable. Here are some examples. We could have, say, an unknown number of customers that enter a store, and each one is going to purchase an unknown number of units of a product. And we might be interested in the total number of units that are purchased by all the customers. Here's another one. We could have an unknown number of insurance claims that occur during a certain period, and each one is going to have an unknown amount paid for each of those claims. But as the insurance company, we'd be interested in the total amount paid for all of those claims. Finally, we might have an unknown number of jumps in a stock price, and each jump will have an unknown amount of change, and that could be positive or negative. But we'd of course be interested in the total price of the stock, which includes all of those jumps. Notice the similarities. Each of these situations has a number of things that we're adding up, and that's known as the compounding distribution. Obviously, it's going to be discrete and integer valued, and we could use something like a Poisson, a binomial, a negative binomial, or any other discrete integer valued distribution to model it. The second thing is that they all are looking at adding up something for each of those units. And this is known as the secondary distribution. It could be absolutely anything. In the first case, it's discrete. In the second, it's continuous and positive. And in the third case, it's continuous and could be negative. So that secondary distribution, the thing that we're adding up, could be absolutely anything. Finally, in all three cases, we're looking at the total. So the sum of each of the things in green and the number of things is what was in blue. So we can formalize this. If we let S equal x1 plus ... plus xn, where n is that compounding distribution, and we have a few conditions. Xi's, they're going to be independent and identically distributed. N is a integer valued and non-negative random variable, and n is going to be independent of those xi's. If we have all of that, then we say that S is a compound random variable. So essentially, it's a random sum of random variables. We'd of course be interested in finding the mean and variance of this compound random variable. So if we want E of S, that's E of the sum as I goes from 1 up to n of the xi's. But how do we evaluate that? We have multiple random variables going on here. N itself is random, and each of those xi's is also random. So how can we deal with this? Well, we can use the power of conditioning. We can condition on capital N equals little n and see what we'll get. So E of S given n equals little n, we can write that as E of the sum, as follows, and now we can use those properties. So we can replace the big N in the left with little n using substitution. Then we can notice that the left-hand side and the right-hand side are completely independent because n is independent of the xi's. Well, by linearity of expectation, we can take that as the sum of E of the xi's, and that's just n times E of 1x because those xi's are all identically distributed. So that's really neat. And that tells us that E of S given n, the random variable, is going to be capital N times E of x. Remember what we do here is we take that same function, little n times E of x, and replace little n with big N to get the random variable. And thus, by double averaging, we can find the unconditional mean of S. We take E of S as E of S given n. Well, that's just E of n times E of x. We can pull the E of x outside because it's just a number, a constant, and we'll get that the expected value of the compound random variable is the expected value of n times the expected value of x. Now think about that for a second. That should make logical sense. If we know that on average E of n customers are going to show up in a store, and each one is going to purchase E of x units, then on average we would expect E of n times E of x units to be sold. So it makes a lot of logical sense, and we got that using double averaging. So we can employ a similar approach to calculate the variance of S. We're going to condition on n equals little n, and we'll get that the conditional variance of S given n equals little n is the variance of the sum of those xi's conditional on n equals n. Well, again, we can use substitution and change that big N in the sum to a little n. We can use the independence of the xi's with n to drop that condition. And then we can also use the fact that the xi's themselves are independent from each other. So the variance of the sum is the sum of the variances. There's no covariance to worry about. And that's just n times the variance of a single xi because they're identically distributed. So fabulous. And that also tells us that the random variable, var of s given n, is capital N times variance of x. Well, that allows us to use the conditional variance formula to find the unconditional variance of s. So var of s is e of var of s given n plus var of e of s given n. We can sub in the values we got there, n times var of x and n times e of x, which is what we got earlier when we were doing the mean. And then, using linearity of expectation, we can pull the var of x outside, and when we pull the e of x outside there, we have to square it when we're pulling it outside of the variance. So that actually gives us our formula for the variance of s. We can split that up into two parts. That first part there is randomness coming from the variables being added up, that secondary distribution. And over here, we have randomness coming from how many variables we're actually adding up in the sum. So that's the variance coming from n itself, from the compounding distribution. And altogether, that gives us the unconditional variance of s. Let's look at an example. Suppose we have the number of customers that enter a store follows a Poisson process with a rate of 10 customers per hour. And each customer is going to spend an amount of money independently of each other that is exponentially distributed with parameter 1 over 100. I want to find the mean and the standard deviation of the total revenue from this store, from all the customers, in an 8-hour day. So think about this for a second. Think about both how we could do this and whether we should. Does it really make sense that each of the customers would be independent and have the same distribution? Does it make sense that the number of customers is independent of how much they spend? Like maybe if the store is really, really busy, customers will spend more, or maybe they'll get frustrated and leave. So you always want to consider whether the assumptions for the model that you're using are actually met by the situation in real life. Here we'll assume that the conditions are satisfied and we can proceed. So let's suppose we're going to let n equal the number of customers in the store in an 8-hour day. Now, obviously, n is going to be Poisson with parameter 8 times 10, so 80. And we'll let xi equal the amount spent by the ith customer. And we're actually told the distribution, it's just exponential with 1 over 100. And then finally, s is just this random sum, x1 plus dot 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 plus xn, capital N there, which is the total revenue of all of these customers. So we can see here, by the definition, is that s is a compound random variable. And we already know that e of n and variance of n are equal to 80 because it's Poisson, and e of x is 1 over the parameter, so 100, and variance of x is 1 over the parameter squared, so that's 10,000. So we have all of the ingredients to calculate the mean and the variance of our compound random variable. We'll get e of s is e of n times e of x, which is 80 times 100, or $8,000. And for the variance, it's a little more complicated. We have e of n times variance of x plus e of x squared times variance of n. Put in all those pieces, we'll have 80 times 10,000 plus 100 squared times 80, which is, I guess, 1.6 million. And if we take the square root, the standard deviation is $1,265. So that gets us the mean and the standard deviation of the total revenue in the store in 8 hours. And we can see that the variance is influenced both by the means and variances of both the distributions of n and the xi's. There's something else that we can do. We can actually get exact results for this compound distribution using MGFs, which is really, really cool. From above, we showed that we can easily find the mean of s and the variance of s just using the means and variances of the individual random variables n and x. But we might want even more information. We can actually find the exact distribution of s using these moment-generating functions. We can write the moment-generating function of s as the expected value of e to the ts, which is the expected value of e to the t times the sum of those xi's. And again, we're not sure what to do with this because we have so many random variables going on there. We've got capital N and all of those xi's all mixed together. So what can we do? We can use the same trick as before. We'll condition on capital N equals little n and see what we get. So we can have the conditional moment generating function, which is expected value of e to the ts given n equals little n, sub in the definition of s there, and then manipulate it as before. Using substitution, we can turn that big N on top into a little n, and then using independence of n with the xi's, we can actually drop that condition. So we have independence, and we can then ignore the condition that n equals little n. Well, that's just equal to the expected value of the product of e to the t xi's, and by independence of the xi's, we can break that expectation up into the product of those individual expectations. Each of those, by definition, is the moment generating function of x1 through xn, and since they're all the same, all of these xi's are identically distributed, so they have the same MGF, that's just the MGF of one of the xi's raised to the power of little n. And because we know that, that tells us that the moment generating function of s given n, which is the expected value of e to the ts given n, remember this is a random variable, that's just going to be the MGF of x raised to the power of big N. Again, we're taking that little n and replacing it with a big N. So now we can use double averaging to find the unconditional MGF of s. It's the expected value of e to the ts, so that's e of this conditional MGF. While subbing in, that's the expected value of mx of t all raised to the power of n, and we can manipulate this ever so slightly. If we let mx of t just equal e to the ln of mx of t, that doesn't change it, so we have e to the ln of mx of t times n. Well, that is just the moment generating function of n evaluated at the ln of mx of t. So this is what we end up with for the moment generating function of s. It's the moment generating function of n evaluated at the ln of the moment generating function of x. So it's a moment generating function inside a moment generating function to give us our moment generating function of the compound random variable. If we actually recognize the resulting moment generating function, then that actually tells us the exact distribution of the random variable s. Not just the mean and variance, but everything we could possibly want to know about it. If we don't recognize it, it's still fine. We can still use it to get the mean and variance by taking derivatives and setting t equal to 0, but it has the opportunity or the potential to give us way more than just the mean and variance, which is what the earlier formulas gave us. Let's look at an example to see how this works in practice. Suppose we have n as a geometric random variable with parameter p, and the xi's are exponential with parameter lambda for I equals 1 up to n, and they're going to be independent. And we'll let s equal the sum as I goes from 1 up to capital N of these xi's, and we're interested in the distribution of s. See if you can think about this and try to find the moment generating function of s using the technique we described earlier. Give it a try, and then you can follow along with the rest of the video. We know, or we can look up, that the MGFs of a geometric and an exponential are nice closed functions of t. So mn of t is pe to the t over 1 minus e to the t times 1 minus p, and mx of t is lambda over lambda minus t. So that tells us that we can use the moment generating function of s by taking the moment generating function of x, taking the ln of it, and then plugging that into the moment generating function for n. So we'll see what we get. We'll take the p e to the t, but instead of t, we'll have ln of lambda over lambda minus t, and then same thing on the bottom there. We'll replace the t with ln of lambda over lambda minus t. Well, look at what happens there. We have e to the ln of something on the top and the bottom. So that will just become p times lambda over lambda minus t all over 1 minus lambda over lambda minus t times 1 minus p. Well, we can simplify that a little bit. We'll get p lambda over lambda minus t minus lambda times 1 minus p, just basically multiplying through top and bottom by lambda minus t. And we can simplify that even further to get p lambda over p lambda minus t. Well, this actually is the moment generating function of an exponential with parameter p times lambda. And since MGFs uniquely determine the distribution, that means s, our compound random variable, has an exponential distribution with parameter p lambda. This is so neat. We took a geometric number of exponential random variables and added them up, and that gave us another exponential with a parameter of p times lambda. So cool. So if we wanted to, we could find whatever we like from this. We could find the mean and variance of this random variable, and you could actually check that you'll get the exact same thing if you use the formulas, but we can also find more. Because we know this is exponential, we could find the probability it's bigger than any particular value. We would know it has the memory list property. We would know everything we would ever want to know about this compound random variable S because we found its exact distribution, not just its mean and variance. So give that a try. See if you can find the expected value and the variance of S using the formulas before for the mean and variance of a compound random variable. You should get these values here. That is everything for this video and for this week and for chapter 3 and the first half of the course. So over reading week, you can hopefully have a look at some of this stuff. We'll have a tutorial when we come back looking at some of these techniques, and then we'll move on to my favorite topic in the course, which is Markov chains. Have a wonderful break, and I will see you afterwards.